Now we will look at how to determine the equation of a plane. A plane in space can be uniquely identified if 3 points on the plane are known, as in 3 points in terms of x, y, and z. Next, if two lines on the plane are known, so you can assume the plane is like a piece of paper, yeah, and then there are two lines on it, okay. And next, 1 point on the plane is known, and a normal to the plane is also known. Normal, yeah, okay, a normal that is being shown here to the plane. The plane is a surface like a paper, and then a normal is a line that is 90 degrees to the plane. Suppose that relative to a right-handed set of axes, we have a plane called pi. So as the diagram shown below, this is the plane which is known as pi, and point P lies on the plane, and the point P coordinate is represented as x, y, and z. So you can see this is point P. It is located on the plane which is known as pi. And let vector A be ABC in component form, and this vector is normal to the plane. As you can see, the vector A is normal to the line QP. So therefore, QP is perpendicular to vector A, or vector A is actually perpendicular to QP. Same either way because they are 90 degrees apart. So QP is written as P minus Q, obviously. And since it's perpendicular, therefore, since QP and A is perpendicular, so the dot product obviously has to be a 0 based on the basic properties of scalar of a vector. So next, since QP is P minus Q, we write it such A dot product P minus Q equals to 0. Therefore, because of the commutative law, A dot P minus A dot Q equals to 0. Therefore, since A and Q are fixed, AQ is a constant on the plane. Because vector A and Q, we fixed it in advance for the purpose of the calculation. So therefore, A dot product with Q is known as a constant on the plane. Therefore, we assume AQ is equivalent to constant K, and we substitute AQ with K into the equation just now. So A dot P minus A dot Q equals to 0. So A dot P minus K, because AQ is substituted with K. And then in that case, AP will equal to K, which is the constant of equivalent to A dot Q. So if we know the normal to vector A and any point P, we can easily compute the K. Provided we know the normal A, as in the component form of A, and also point P, which is XYZ, and we can compute K. So this is how we derive how to determine an equation of a plane. Right? An equation of a plane should equal to the dot product of ABC and XYZ, which will be A multiplied by X plus with B multiplied by Y, C multiplied by Z, and it should equal to K. This is an equation of the plane pi that we have been discussing from just now. To find an equation of a plane, so as a conclusion, we must be able to reduce whatever data is given or information given in a particular set of a problem, that the components of a suitable normal vector means we must have A, B, and C, which are components of a normal vector, and we need obviously X, Y, Z, which is a point on the plane. So for example, if you are given 4 points, which are P, Q, R, and S, and you're required to find the equation of the plane perpendicular to PQ, which contains the point P. So in order to find an equation of a plane, you need two things. The first thing is you need a vector which is normal to the plane. So here is said that find the equation of the plane perpendicular to PQ. So if it's perpendicular to PQ, so vector PQ will be the normal to the plane. Your first step would be finding the vector PQ, which is normal to the plane. So PQ is identified by using the formula Q minus P, right? And then you minus the X and X, Y and Z of Q and P respectively, and you will arrive to the normal vector, which is 1, -1, -7. These are the components of X, Y, and Z respectively. And you have to identify the second item, which is the point, which is related. So here is clearly stated it is point P. Therefore, you consider point P for the K calculation. Recap back, K is always a product of the normal vector to the plane, which we have obtained just now, 1, -1, -7, and the point that the normal goes through, which is clearly stated here, it has point P. The plane has point P. So we multiply both of this and we will get a number. So we have got K as -22. Now we need to write out the plane equation. So we can simply write out the plane equation by taking 1, -1, and -7 as the components of the normal vector to the plane, which is x minus y minus 7z, and it should equal to k, where k is -22. For part B, we are required to determine which of the other points lie on the plane. So we have used point P and Q in our calculation, and we have obtained the equation of plane. So it's very obvious point P and Q are the points that are related and lie on the plane. So next, we have to only test whether point R and point S actually lie on the plane. So what you need to do is, in order for the point to lie on the plane, it has to satisfy the plane equation, which you calculated earlier. So substitute x for point R, substitute x as 1, y as 1, and z as 1 into the vector equation. And obviously 1 minus 1 minus 7 is not going to give you a -22. So therefore, point R does not satisfy the plane equation. So therefore, point R does not lie on the plane. S, on the other hand, has 7, -6, and 5 as respective value of x, y, and z. When we substitute into the plane equation, you will actually get a -22. So point S satisfies the equation. Therefore, point S actually lies on the plane. Find the equation of the plane which passes through the point A, B, and C. So you need to find two things to find an equation of the plane. First is you need to find a normal to the plane. Second is you need to use a point that is on the plane. So in this case, you have got 3 points and you need to find a normal to the plane. The first step, yeah. So two vectors that lie on the plane, which are in this case, say for example, we take AB and AC, and obviously AB cross product with AC has to be a normal to the plane. This is by theory, yeah. So in this case, you find vector AB, all right. You find vector AB by point B minusing point A. Okay, and then you'll get 2, 1, 3, right? And then vector AC is simply by C minusing A, all right? So 2 minus -2 and so on, right? And you get AB and AC respectively. And next, you need to find the normal vector. So you proceed, you find the cross product of AB and AC. So when you determine the cross product of AB and AC, use the shortcut method. AB and AC has 2, 1, 3 and 4, -2, 1 as XYZ component respectively. So you need to add IJK at the top. All right, use the shortcut method. All right, recap back. I have explained it in the previous set of slides. Okay, so in this case, you apply the shortcut method, and then you will get, because this is a cross product, so recap back, you should actually get a normal vector. A normal vector has to have the component of x, y, z. So this, it will be 7i plus 10j minus 8k. Next, you need to find any point to actually determine k. Okay, how do you decide which point? So go back to the two vectors that you used just now. You used vector AB and AC. So you always have to use a common point in both of the vectors that you use to do the cross product. So you did a cross product between AB and AC, and the common point in both AB and AC is obviously A, because A appears both in AB and AC. So therefore, to determine K, you use point A. So how to determine K for a plane equation? You simply multiply the normal vector with the particular point A. The common point in the cross products is A. So you multiply 7, 10, negative 8 with negative 2, 1, and 2. So when you multiply, and it's a dot product, you multiply it as a dot product. So it's 7 times negative 2, you get negative 14. 10 multiplied by 1 plus 10. And negative 8 multiplied by 2 is my negative 16. So you add this up, and it has to be a scalar product because it's a dot product. All right. And you get a resultant as negative 20. So once you get the value of k, and you have the normal vector, which is 7, 10, negative 8, you can write down the equation of the plane. So the equation of the plane is simply 7x plus 10y minus 8z equals to the k value, which is negative 20.